Today we're going to talk about how do we solve rational inequalities. And so an example of one is right here. When you have rational inequalities, you do need to make sure that you notate that this is going to have a domain restriction. Because you have an x plus 2 in the denominator, you have to make sure that you annotate that x cannot equal negative 2. That's going to be a domain restriction. With these, as long as they have a 0 on the right-hand side, we can go ahead and start to identify where our boundary points would be. And the boundary points would be any zeros that we would get from the numerator or the denominator. Now, in this case, the numerator is just a 5. So there aren't any zeros or boundary points that we're going to get from the numerator. But for the denominator, I'm going to have a 0 at negative 2. So in this case, I only have one of them. So I would draw my number line. And I only have one boundary point at negative 2. Now, usually, I would look at our symbol here and say, well, that's going to be a closed dot. But I have to keep in mind that I have a domain restriction that x actually can't equal negative 2. So I'm going to have an open dot on this one rather than a closed, all because of the domain restriction. From here, just like in our quadratic inequalities, we're going to test each side. So I'm going to test a negative 3 for numbers less than negative 2, and I'm going to test a 0 for the ones bigger. If I plug in negative 3 to this left-hand side of the rational inequality, I would end up with a 5 over a negative 1, which is a negative result. If I plug in a 0, I end up with a 5 over 2, and that's a positive result. We have a greater than or equal to sign, so my arrow is going to go towards the positives. So this is what my graph would look like. For answering these, we're going to stick with interval notation. So I would have a parenthesis and then the negative 2, comma, infinity, also with another parenthesis. So this one's unique that it only has one boundary point, and then that boundary point happens to also be a domain restriction. So in this case, we don't have any square brackets, even though initially we thought we might. Okay, here is another example. It starts off with a 0 on the right-hand side, so that's good. We can go ahead and start to identify our domain restrictions. For the domain restrictions here, 4 minus x squared cannot become 0. Now, you can either solve that or you can reason through it, and you're going to get that x cannot equal both positive and negative 2. That's the domain restriction. From here, you're going to identify zeros from the numerator and denominator. So this time, my numerator does have a variable in it. I have x plus 1. So one of my zeros is going to be x equals negative 1. I also know that this denominator factors. The denominator is going to be 2 minus x times 2 plus x. It's a difference of 2 squares. So I'm going to have zeros at positive 2 and negative 2. So in this one, I have 3 boundary points that I'm going to put on my number line. Make sure you do number them least to greatest on your number line. So the first one would be negative 2, followed by negative 1, and then followed by 1. So now we're going to test each of these sections. So I'm going to test a negative 3 for in here. Now for in between -1 and -2, I'm going to test a -1.5. And remember, decimals are fine when you're testing your regions. Just don't use them in your final answer. Between -1 and +1, I'm going to go with 0. And bigger than 1, I'm going to go with 2. And again, you are putting these into the, let me erase this. Whoops. Maybe it won't let me click on my eraser. You're putting it into the original rational expression. So if I put in a -3, the numerator would become a -2. And then that denominator would be 4 minus 9, which is -5. So this ends up with a positive result. I'm going to do the same thing with my -1.5. I'd end up with a -0.5 over, and then I'm just going to use my calculator. Just make sure when using the calculator, you have to put your -1.5 in parentheses before you square it. Otherwise, the result is not going to be accurate. And this gives me a positive 1.75. So that's a negative result. If I plug in 0, that's going to be 1 over 4. So that's positive. If I plug in a 2, that's going to be 3 over, oh, I used a wrong number. Let's see. This isn't a 1. That's supposed to be a 2. About to say, I'm going to run into a domain restriction here. This should have been a positive 2. So I'm going to test a 3. So let's see, that's 4 over -5. So that would have a negative result. Now, for your points, we have a less than sign. So they're all going to be open anyway. So I don't necessarily have to worry too much about this domain restriction because they're all open anyway. So I have open dot at -2, -1, and 2. And because I have a less than inequality, I'm going to go towards the negative results on my number line. So that would be connecting these two, and then the 2 would have an arrow going to the right. So the final answer for this one in interval notation would be parenthesis from -2 to -1 with another parenthesis, and then we're going to have a union from +2 all the way to infinity. Okay. The next slide, we're going to talk about some special cases. So these are interesting because when I go to find my zeros, right, in the numerator, I get x equals 0. But in the denominator, these would be imaginary zeros. And we are only going to work with the real zeros. So I can try to do a number line, but something really interesting is going to happen. You can actually reason through this without the number line. If you think about the fact that the result of squaring anything is always positive. Okay. And then let's look at the denominator. The result of x squared plus 1 is also always going to be positive. So in this case, the only thing that's going to throw that off is a 0. Okay. So I really need to do this. This really needs to have an equal to bar on it. 0, when I plug in any number, my numerator is always going to be 0 or a positive. That denominator the smallest value it could possibly be is a positive 1 after I'd squared any number and then add 1 to it. So it's going to also always be positive. So I want to think about this result here. This is always going to be true. Any positive number is always going to be greater than or equal to 0. So in this case, this is an all real numbers situation. And in interval notation, we would notate that as all the numbers from negative infinity up to positive infinity. This case would be true. Now, if that equal to bar wasn't there, then we would have a weird condition, because if x is 0, 0 is not just greater than or equal or greater than 0. So it causes some trouble there. So that's why we had to have that equal to bar there. Okay, well, what if we flipped the symbols? Okay, what if it was less than 0? Well, this is really kind of the same situation, right? No matter what, that numerator is going to be positive. No matter what, that denominator is going to be positive. Right, now that numerator can equal 0. That's a possibility if x is 0. But regardless, the result of x squared over x squared plus 1 is never going to turn negative. So this is one of the special cases of no real solution. It's not going to be possible. And so in scientific notation, we notate it as the null set. And so it's just a circle with a line through it. And that's null. And that would be our answer. Or if you wrote no real solution, I would take that too. That's what it looks like in interval notation. And that is solving rational inequalities. Just be careful with your special cases. They're going to pop up every once in a while.